Hi. Okay, so I I had a pretty good time making the video to describe my structure modeling thing last week, and um, I kind of felt like I wanted to make some follow-ups, giving more real-world examples if I came across a chance, and it just so happens that stuff that I'm doing in 4coder that I've been doing in 4coder for the last couple of days exactly matches the pattern, and so I decided to turn this into a chance to do a series of videos. I'm going to try to record them all back to back here, but I'm going to try to keep them short and concise, unlike the intro video, which is kind of long and sprawling. Um, so hopefully that makes it more convenient to watch. I think it'll also help me stay focused and on topic, and give me a chance for breaks in between and stuff. The um, the code I'm working on here is all going to be part of the new 4coder beta, so it'll all be public soon enough for people who have the 4coder beta, and it'll also all be developed somewhat before your eyes. But I've already done several stages beforehand. First of all, the part of the process where I understand the problem, I did that years ago when I wrote the first and second Lexer for 4coder. The first one was just a handwritten, consume some characters, try to figure out how far to go, like how far to advance your like pointer cursor thing, and emit tokens as you go, using like functions that implement different cases and stuff. The second one was inspired by Sean Barrett's unfinished, hidden little paper about lookup table accelerated state machines for lexing, which is a technique where you take the idea of the like implicit state machine that is formed by the code you write in the handwritten one, and you reconfigure it so that each stage of that lexing process is written as like a formal state machine. There's a state, you read an input, you do a transition to another state, you read an input, you do a transition to another state. The only catch is there are certain points at which when you do the transition you also emit the token for that transition. And you put that together and you have a lexer that basically runs in a single loop. For every character it has to take the input character, look that up into a table that converts characters into equivalence class indexes, take the equivalence class index, combine it in the right way with the state index to look up into the state transition table what the next state should be, and set the state with that, and then you also look up into another table whether or not you need to emit a token or something like that, essentially, or what type of token to emit. You have some kind of method for encoding either in the same table or in a second table that's parallel what action you need to do in terms of emitting a token. So I handwrote one of those, or rather I handwrote one of those, and then I wrote a somewhat over-bloated and not well organized like hybrid solution that it automatically generated some of those tables, but it had a bunch of tables because I had sort of issues with the tables not being quite identical in certain major states. And then there was confusion, like for me I didn't want to write the whole thing as a state table, because if you write it so that you have the ability to, for instance, determine keywords and processor directives, then you're assigning basically every single character to its own equivalence class, because now you have to use a state machine to detect keywords. Now you have to use a state machine to detect preprocessor directive word like names. You still have to write the whole, like, everything for integers and floats has to all get combined, so 0 is different, A, B, C, D, E, and F are all different because they're also part of hex. 8 and 9 are different from the other digits because they're not a part of octal. The period is really complicated. There's just a very complicated state machine that goes into that, and trying to turn that whole thing into a lookup table would have made the whole thing too bloated. The whole advantage to the lookup table is only really realized if you manage to keep the number of states and equivalence classes fairly low. If they get to the point where the memory lookups are costing you a lot, you would have maybe had faster code if it had just been doing inline comparisons and jumps the way a handwritten one does. But it is a fairly convenient way to write it if you can get your tables at the right size. So what I had to do was sort of hand roll portions of the Lexer that would decide what major state you're in, and then you use a different lookup table for which based on which major state you're in. Now, you don't have to go that far if you don't try to handle everything in the state machine. For instance, keywords don't need to be handled in the state machine. You can just parse them as identifiers and then do a separate pass or a separate like check in the loop or something that says if you emit a keyword, look it up in the or an identifier, look it up in the keyword table first. You can have all preprocessor directives just be labeled as the same token type preprocessor directive, and then do a secondary pass to look up which one they actually are if you need to do something like that, or again do that as a separate check inside the main loop of the lexer. So those don't have to be that complicated, but there's still, like, if you're inside a preprocessor body and you want to parse the word defined there as a keyword, but when you're not in a preprocessor body you don't want to parse the word defined, or better yet, operators. If you're in a preprocessor body, you want the pound and pound to be the stringify operator and the concat operator that are available in macros, but you don't want to parse those as operators outside of preprocessor bodies. You now need like an entirely separate state for everything that you had a basic state for. You need a state that is the same identical thing, except that it remembers that it's in a preprocessor body. Instead of doing that way, what I would do is just say, okay, we've transitioned into a different major state. We're in a preprocessor body, use a different table. This led to there being like about 5 or 10 of these tables, because I also wanted like a separate table, for instance, for the float and integer parsers, because those are fairly complicated all on their own, and they, as I was saying, if you're parsing hex, it changes what letters mean. All of a sudden, A, B, C, D, E, and F, lowercase and uppercase, can't have the same exact set of behaviors as all the rest of the alphabet, because they have a special meaning in a particular part of the state machine. On the other hand, if it's a separate state machine that encapsulates or like separates or isolates, I guess is the word, it isolates that strange behavior, that's a little better. So point is that I've sort of spent a lot of time tweaking and learning about how to structure that the way I want it, and in the end it just was really hard to modify, and it also was not really amenable to extension to other languages. So the new 4coder token system I've been developing is basically, it features like a 2-layer token typing thing. One layer of the token types is meant to be generic for all languages, so that you can have basic types that are like, this is a scope opener, a scope closer, a parenthetical opener, a parenthetical closer, a single thing that just says keyword, a kind that's just keyword, a kind that's just white space, a kind that's just comment, basic stuff. And then the per language, there's a separate kind field in the token that lets you have per language semantic stuff if you want it. So the point there is there are lots of features in 4coder that just need a very vague idea of what the language or what the tokens look like. And to avoid having to rewrite all that basic stuff for every language, I decided to make a generic token system that would allow you to say this token has this basic kind. So in code that only runs on basic types or generic token kind information, this is how you should treat it. And then you have a separate field where you can put in the language specific thing. So your keyword can then be differentiated by, oh, this is a keyword, it's the size of keyword, right? So if you're in C++, you know which type of which keyword it is. But if you're not in C++ and you're just doing token highlighting and you just want to be like, is that a keyword? Do I do the keyword thing for that? Then you can just check the base field. So that's the new design of the token type, and so it needs a new lexer, because the old one, as I was saying, wasn't really easy to modify. It was very C++ centric. Trying to make it cooperate with this new one felt like it was going to be more work than it was worth, because especially because I want to broaden out 4coder support in the future anyway, so having like a very weird special case for C++ seems strange. So I just felt like it was time to write a new lexer for 4coder. And when I did that, I sat down and the first thing I did, so that's phase one, is I understand what I want to create. The first thing I did was I sat down and I wrote all the code that describes the model that I wanted. Now I knew I wanted a state machine, and I knew I didn't want to hand optimize which parts of the state machine are isolated from other parts in the lookup table accelerator. Right? I want that to be something that I don't have to think about. So if it means that the whole thing can't be it can't be lookup table accelerated in the end, then fine. We'll just make a state machine that does control flow. It's implemented as a control flow state machine instead of a lookup table state machine, if that's what it has to be for me to get like a reasonable size output code and performance. If I can't find a way to write an optimizer that does the table isolations in the right way, then we'll try to do a table-driven one. We'll see what happens. Either way, I haven't decided what the backend looks like at this point. I just wrote out the entirety of the model, and I did that without even the code that would construct the model, and that was a pretty cool experience. It took about I mean, my handwritten ones have always taken a long time, and I'm sure that it's not exactly correct, the one I have now either, so it's going to take a long time to tweak and adjust, but I think it was the fastest I've ever gone from scratch to having a fully written out C++ Lexer that does, you know, operators, keywords, integers, floats with their like exponent suffixes correctly, with the like integer suffixes and float suffixes correctly, with the string parsing with the prefixes done correctly and the raw strings done correctly, escape sequences done correctly, you know, just you name it, all the things that are potentially difficult, hex and octal. Like when you see a 0 and you're lexing, it's actually fairly intricate. You have to like have a special state for I just saw a 0, because that could be a lone 0. That could be the beginning of the next thing you see might be a decimal point, in which case it's a float. The next thing you see might be an X, in which case it's hexadecimal. The next thing you see might be like an octal digit, in which case it's octal, right? So there's a lot of things a 0 can turn out to be. The same thing happens with period. When you see a period, it could be a period like a dot operator. It could be the beginning of a C++ member operator, like the dot star and dot. It's like dot star and arrow star, I think, or something like that. So it can't be the beginning of arrow star, I guess. But it could be the beginning of dot star, and it can also be it can be the beginning of a float. So there's various parts of the state machine that are just somewhat intricate to write out by hand, actually, that are actually really easy to write out, or at least easier to write out in a state machine, at least the way I did it when I sat down to do that part. And I felt like that went really well, so that was about 4 hours of work that didn't get recorded for you. I'll just show you the result of that by the end of this video. So there's the state machine without any of the constructor functions actually being implemented. I just wrote out like, here's the case, here's the here's the state, here are the case handlers for that state, here's the state, here's the case handlers for that state. Just making it up as I go along, trying not to invent too many features so that it would be easy to implement, but always inventing a feature when I felt like it would be harder not to, or impossible not to. Then, in about 5 hours of work, I wrote all of the code that does the construction. So I am now able to correctly construct the model in memory that the initial code I wrote was trying to communicate. So there's like step 1, just communicate out, get written down somewhere in a format that I can use later easily. What is the information that describes the lexing of C++? Second step was, what is the code that makes the format I wrote out of my head that didn't compile before into code that does compile and that constructs in memory the graph that is that state machine, right? Like, it's more than a graph, it's a state machine structure, but essentially the interconnected set of node types that need to be used to represent the state machine are now constructed in memory when you run the program. So the next stage is to write the entire codegen part, and that's the part that I think is the most that's the part where the most interesting stuff happens. You can do optimization there, you can do like decisions about how the generated code integrates into your system, right? There's a lot of fun stuff that happens there. The modeling part, I don't have like I feel like that's the part that is initially you just are writing down something and you're hoping you're getting something close to useful, and you won't get a chance to test it until the whole system's up and running and you start tweaking it or trying to write a second model on the same modeling structure as the first model was written on or something, right? But the code generation part, you get to print out code, you get to see your code getting printed out, you get to see the structures that you are like so far just been abstractly manipulating in your mind, translated into hard quality code that you can bake into your project. That's the part that I enjoy the most. So that's what we're going to be working on throughout this series of videos. And with that intro out of the way, I am now going to take the second half of this video to introduce you to the features of the state machine model that we're going to be implementing today, so that you're up to date with me, and then the next video will start the actual programming. This is just an intro to the series, and the best place to start on this intro, I thought, was, besides that intro of what the series is about, is the description of the model, the mathematical, almost semi-mathematical description of my state machine model. And then I'll show you what the code for the model looks like, to make it a little more concrete for you. But you need to understand this model in order to understand what I'm implementing a code gen for. If I don't understand what the model is supposed to mean, then I don't have any way of understanding what it's supposed to output when I write code out from it. On the other hand, if we know what the model means, we have a shot at generating code that does what the model intends to do. So the state machine has the following features. First, its alphabet is fixed. Its alphabet is just any value of a single byte. So anything between 0 and 255 is a valid input in the input sequence. There's one caveat to this, actually, that I should have written in here that I didn't. Maybe I should extend this real quick. Yeah, is that in addition to that, in addition to everything in that range, the other possible input is end of file. Whoops. I hate Paint when I'm trying to do boop e equals 255 and end of file. Okay. So in addition to having all the numbers of a byte, which are valid, considered valid input values, it also has the input end of file. Now the input end of file is not encoded in a string. I mean, you could encode that as like a 0 or use the end of file character from ASCII, but I'm encoding that as a separate concept. There's 0 through 255 are the bytes that can come in, and I can send down basically, it's not a byte, rather it's a different type of event that can be sent into the state machine that says, hey, we've reached the end of the file. And the way the state machine is defined, it doesn't have exit states, it does not have halting states. Rather, the calling code that is pumping things into the state machine knows that the state machine should no longer receive input when it has passed down the end of file event. And the state machine can do any of the things it can normally do on any other event on an end of file event. It can generate tokens, it can do whatever, which is important for the design. There's our extended alphabet that we're actually using. Alright, so what are states in the state machine? A state can basically is somewhat generic. It doesn't have a lot attached to it. There is something that's directly attached to the state that I haven't listed out here, but that's because it's essentially syntactic sugar, or like a slight abstraction over a simpler concept that we're going to immediately reconfigure as we start going to optimizing and generating code off of this structure. So we'll just imagine that what a state actually is a little simpler than it will be when I show you the modeling code, but then I'll explain when we're looking at the modeling code why the one feature states have isn't actually going to be a feature on the states for very long in our process today. So a state queue is just that. It's nothing else to it except that it's a state, and each state is distinct. The user defines all the states. There's only one special state, and that's the root state or the initial state or the entry point, whatever you want to call it. And that's just the one that is the state the state machine is placed in when it has not got any input yet. Before its first input, that's the state. So that's all the states are. There's also a concept of flags in the state machine. So every flag is the user defined, and a flag is essentially like a variable that will either be a 0 or a 1. It's a bit, this allows me to essentially, sometimes when you're building a state machine, you get, like I was saying, the idea with the preprocessor, you get to a point where you're like, I want to do this I want to do this whole state machine. I want to have all the same behavior, but I want to remember that I'm currently in a preprocessor body and not in like normal code, so that I can do this one different thing. Well, that would normally, classically, without flags, require you to copy, or any other type of variable, require you to copy all the states so that you can do all the things other states do without forgetting that you're in a major state that's different. You're in a situation where there's one spot in the copy that's a little bit different, and you need to be on this side of the path until something bops you back over there, right? And I don't want to have a proliferation of states if I can avoid it. For a bunch of reasons. One, it's harder to write the model that way. Two, it's harder to optimize because, like I was saying, the lookup table system really requires you to isolate these types of things. And I think by encoding these ideas as flags, I've found a way that I might be able to hopefully, I mean, so there's always the possibility that the best way to end up implementing flags is by doing the copying under the hood of that whole state structure, right? And then reconstructing a new state structure that has the one quirk in it that it needs to have, and then optimizing these two state structures together as one state machine, right? Where there's like the 0 value of the flag and the 1 value of the flag are the two nearly parallel state machines with slight differences in them or something. So that's a possibility that we might end up needing to do to get the most optimal thing, but there's also a very good possibility that and I think more likely possibility that the correct way to generate this is going to be to literally emit like variables that we will be setting flags on, like bytes where we can manipulate flags and do flag checks. We'll have to be careful that our flag checks aren't always being executed, but are in some way control flowed into in the situations where they are relevant only, and then are checked, right? But that's not necessarily going to be that complicated when we get into doing it. So that's what a flag is. From the perspective of the model, it's a 0 or 1 variable. It's a variable that contains a 0 or 1 that it can set and that it can read as part of a transition between, like, on an input, essentially. So in addition to the flags, the state machine system also has what I call actions. Now, actions are basically things that do not directly involve so the lowest level part of the state machine is the idea that it's in a particular state, it reads an input, and then it transitions to a different state, right? Based on what it read. Well, before it does that transition, but after it does that read, it can do some other actions first, and those other actions are things that don't involve like reading the state or reading the value directly, but rather involve things that have that are relevant at a slightly higher level in the lexer. So, for instance, the first action is emit a token. And that is set up in a way where basically when you emit a token, you just say what kind of token you want to emit, and it assumes that the beginning of the token is wherever the last token ended, and the end of the token is wherever the current read position is. So when you read something, if you don't consume that first and then you emit, that gives you a token that's one shorter than if you had consumed it and then emitted, right? You can do this consume operation down here that increments your position, and the emit token uses the current position, the value of position, to decide where the token goes. And then it remembers where that position was, so the next token can begin there. So this basically creates a series of tokens that completely covers the input space. This includes white space. So white space between tokens, this was a suggestion from Casey, was that tokens should be perfectly abutting, so that when you ask for a point in a file, you're never between tokens. There's just sometimes you're on a white space token, and if a white space token isn't what you want, you can just iterate left to right to find the kind of token you want. But the idea is you have this set of non-zero length tokens that directly abut each other from beginning to end, and that will simplify some aspects of what I used to have in my old Lexer. Was it would read white space, and it had to have a separate loop for white space skipping, and then once it successfully did its white space skipping, it would jump down into a different loop that would build up a token and emit it. Well, now that can be one thing because white space skipping doesn't happen. White space just gets emitted as a white space token. So there are also like some basic control flow primitives in these actions. So when we create a list of actions we want to do, we can put a label in there, and a label will be a no-op in the sense that it doesn't do anything, but it does give us a position to jump to from operations that have a jump feature. And then these two operations here, or actions I should say, call them, can be in an action list and refer to a label that is also in that action list. So for instance, the flag check is how we take advantage of the existence of these flags. When we are taking actions, we can do a flag check, and that flag check says something like, read this flag, see if it matches this value, and then on success, if these are a match, jump to this label. That's it. It's fairly, fairly standard way to implement a kind of basic jump on a thing, I think. I could have done one where you didn't take in value, where you just do flag, comma, label jump, but I just feel like this is we're modeling it. Our model can be as high or low level as we want it to be, and this is like no additional complexity in exchange for like a lot more flexibility, in my opinion. It's just easy for me to manage this, having the value rather than just saying jump if flag is 1. Now I can also jump if flag is 0 by just changing value to 0, right? The keyword check involves something that I haven't really included in this description of the model, but that's because the concept of a table is almost external to this whole thing, but it isn't quite. So the tables are basically string tables that we will be able to pre-bake, but don't necessarily have to be pre-baked, but one way or another you have to set up the linkage. So if you wanted to have like runtime linkage where you can change the table that is being linked to, you would still need the code that's generated to refer to a name, or to use a name to refer to the thing, and the name it uses would somehow need to bind to that, and so that thing would somehow still need to be generated globally, and I didn't want to deal with all that. So it's actually going to be part of this generator's job to build all of the built-in tables, but there's no, it's not really baked in. The tables are almost as part of a separate universe of this problem, but a keyword check will take in a table, which is a hash table of strings, and it will look between the token and mark and the position. So this happens before an emit. After an emit, that'll be a 0, like it'll be an empty string, right? Because whenever we do an emit, the token mark moves up and it becomes equal with the position. But when they're not equal, they refer to a lexeme, right? So at any time we can just say check the lexeme, and that means the stuff between the token mark and the position so far. So when we've parsed something and we have determined that it's an identifier, for instance, it's not the only case where we'll use this, but if we determine that it's an identifier, we then want to figure out if it's a keyword, and if it is a keyword, what kind of keyword for this language. So if I parse size of, and the next thing is a parenthesis, it'll think so far it has an identifier, but then I will want to be able to say do a keyword check on everything before I emit this as an identifier, because if the keyword check passes, I'll get two things. One, it'll jump to a label so I can skip over the wrong type of emit, right? And secondly, it will give me how's the way to put it? Secondly, it'll give me the ability to say, like, what kind did I get from the check? So when I do a keyword, I guess I'll put it this way. The table has strings and like language-specific kind information for each token. So if I parse the size of and I look it up in a table, that size of slot in that table won't just say yes it exists. It'll say yes it exists and it's the keyword size of, and it'll give me a special enum code for that keyword. Now what I have to do is say, okay, I matched with that keyword size of, and so I know all of the keyword information that I need to generate. Like, I know the kind that I need to emit now is keyword, so I can go ahead and do that, and that is actually baked into the keyword check, right? So if it does find a match, it assumes that the point of doing this keyword check is to do an emit. So it does an emit with the kind that derived from the table, and then it does the jump. It doesn't force me to do the emit myself. So the idea of these here is that it'll essentially let me bisect the set of actions in different ways. I might, and I don't have this, but I might need like a generic jump at some point as well. We'll see. I haven't gotten to the part where this is a slightly lower level than what the modeling code actually looks like. This is like what we're gonna. The first stage of translation is going to be to turn stuff into this. And like I said, there are a few features that are a little different in the model because it's just easier to write them down that way. That I want to immediately turn into this because this will be easier to generate off of, I think. Finally, I already mentioned consume, but that just takes the current position. I didn't put tick marks on it for this time for some reason, but increments it by 1. And then finally, we have the ability to set a flag from the flag field, right? And all of that. So that's like all of the features that you know. We have a set of states. We have a set of flags. We have these concept of actions, and each of these S is the set of all possible states that the flag field can be in. A is the set of types of actions we can have. Using that as sort of our type system, we finally can define the transition function, which is the core of what actually is the state machine code. The transition function is the state machine's code. And that is, given any state, given any character from the alphabet, and given any state for the flag field, so basically the bit string that represents the current flag field, we can put any combination of those three things into the transition function, and what we get out are two things. One, we get a list of an array of a sequence of actions, right? You can think of this as a list or an array or something. So we get one or more or 0 or more of these essentially. And then we also get the transition state. So that's the new state Q. The state the new state, which will be one of the members of this set here, that we will transition to after committing all of those actions. If that makes sense. Now, keep in mind that this is not quite a rigorous definition, because what's actually happening here is the actions and state this transition function is a little bit blurred here, because I'm saying that the actions that are defined here, but that's not exactly true. Some of these actions will be able to appear here and some of them won't, because some of them will actually be used in the process of figuring out which state to transition to. Perhaps a better way to write this would have been if I, instead of stating Q here, I think the reason I chose to do it that way is because that's like a classical way of representing a state machine. But what we might actually be able to say more accurately is that we don't emit the Q as part of this, but rather we're going to bake into the set of actions transition actions that actually do the transition. But it's a bit confusing because there's a requirement that a transition always happens, and that only one transition happens per set of actions. But which state we transition to is determined by the set of actions, so I wasn't quite sure how to state this. The Q is determined by the set of actions, but in theory we could just simulate that set of actions and determine the Q by hand, but in the generated code that's not what it's going to look like, so it's a little bit, there's a blurry line there. I hope that what I just said made sense. It might not, but it's a little bit of a question there where I'm not sure, and I'm not going to overthink what the right way is. I know in my head how these things are roughly going to have to fit together, and it's a good enough understanding for me to move ahead, but it's not quite like this, but it's kind of like this, and it could be like this, but it's not actually going to, this could be used to be the correct thing, but implementation-wise it's not going to look exactly like that. So let me show you the generator stuff. So over here we have, what is this? Oh, that's the wrong okay, I gotta get rid of that language file sooner or later, but okay. So here's the main file, and the idea of the main file is that it defines a bunch of stuff and a main function, and then you just include this file into your other file, for your specific language. So I have my LexGen CP. Maybe this should be a larger font, by the way. Let me restart 4coder to give us a larger font. Okay, let's try this again. Okay, So the idea is you're on this side we're looking at the language specific C++ stuff, and on this side we're looking at the generic generator code. So the generic generator code has like our constructor definitions. Let me see if I can find those. Well, let me start from. I'm going to do this in order. So the first thing I actually wrote was this side, and in particular I wrote basically this stuff here. So we're doing things like naming how we want certain operator characters to be named. There's some of this got pulled up into a generic naming stuff over here too, but originally this was all in line right here. There was like getting an array of the characters greater than, like the values greater than 128 or 127, right? Everything greater than 127 is right here in one array, so that I can easily refer to it. I just call that UTF-8, but that's just a kind of a dumb name. I don't know what might have been a better name for that, but point is, there's, setting that aside, naming characters, which is not a part of the stuff I was just showing you. It's just a part, like a helper. You can see it's even called a state machine helper, not just state machine. So the prefixes are always SM, and then occasionally like there's SM, which is the base API, but then there's like SMH, which are just helpers, and there's also SMO, which are operators. Well, I'll explain why that's like happening more as we go, but it kind of just lets me organize what and mark what the purpose of a function is. And this is, for instance, just something that calls to the actual SM API with stuff that is fairly typical. So naming all these characters, a few of them get renamed differently in C++ from their like generic names. Some typical tokens that pretty much every language is going to need. Lexer error, white space, and end of file are basically going to be one-to-one mapped to the base kinds. As far as I know, maybe Python wants this to be different, right? Python might want white space to be treated more smartly, so it wouldn't be able to use this helper. But like most languages, I think can use that helper. Most languages can start with this helper and rename a couple things. And basically, what this code is doing is declaring different types of tokens that I'm going to want generated. You might wonder why I'm doing this as a generator and not just like why am I not just doing an enum for it. There's a couple reasons. One, I want to create for each of these tokens kinds, so there's like a block comment and a line comment. I also want to have an automating system that says both of these are type base kind comment. So I'm selecting which kind of base token, like which base token kind is associated to each of the token kinds I'm generating. So this and this are now implicitly paired with this because this was the selected kind. This gets implicitly paired with this. All of these get paired with this. And so inside the model, not only do I know the set of tokens I'm generating, but also information about if I match that token type, or if I have like a table that says this is the token type that you want to output in this case, I also know the base kind I want to output at the same time, right? I can pair all that information up internally and write the generated code to be as optimal as it needs to be. So yeah, that's just directly doing tokens. There are also tokens that are defined via operators, and this has sort of a double purpose. One, it lets me build my token like operator tokens by specifying the actual like punctuation that creates that operator, and then it uses unless I give it a specific name. So this is the arrow operator in my tokens. This is the arrow star operator in my tokens. So these are giving explicit names for those pairing that operator to that token name. But if I don't provide one of those, I can just automatically be like, okay, what is the name of this character? Well, if we look here, I named that not. So this is just going to be called not, right? That's the name of the token, is this, not. The name of this token would be dot star, because, let's see, this right here is called dot. Actually, that should probably be like, I don't know, dot might be a good name for that generically. So this is like dot and star, right? Those two names for those two characters. So the name of that token becomes, it's equivalent to as if I had written dot star, right? And so the whole character naming thing, you can rename a character as many times as you want. It's just meant to be a way to like simplify the naming of tokens, make it more compressed and regularized a little bit. So like I can set the character names to left and right for cases where the left arrows are being used to mean leftwardness instead of lessiness, and then I can name them to less and greater when they're meant to represent lessiness and greaterness instead of leftiness and rightiness, and then down here they're leftiness and rightiness again. And then it's just, a handy way to condense the amount of typing I need to do, and also it like couples things that are like, it couples things together that deserve to be coupled together. I want this to be called left equal. Because it's the left shift operator, which I'm calling left up here, that does assignment, right? So it makes sense that these should both be called left and that this should be called EQ, because all of the other things that do like assignment operators, like this is plus EQ, minus EQ, star EQ, div EQ, mod EQ, because up here I renamed percent to mod for this. Oh, slash is called slash, huh? I think I want to rename that to div for C++. Although that could just be. No, I think that's too presumptuous. I'm going to call that div for C++. That'll be a little better. So you see, just by doing that, everything that down here has a slash in it, boom and boom, I renamed them both simultaneously, and I didn't have to go and track them down, except to demonstrate to you that what it would have looked like if I did go and track them down and rename them here and here. I'd have been typing slash multiple places. This is just, this whole operator thing, the first purpose is just simplifying the maintenance of naming for operator tokens. The second thing it does, though, is it also generates, so in addition to generating tokens, and it still has the base kind thing, right? It's still like doing that pairing thing. So these are working just like these did, where this generates a token, this also generates a token and pairs it to this base kind. It has a second purpose, which is you can see I'm putting these all into a particular operator set. So when I begin an operator set here, I'm basically selecting that operator, creating one and selecting it into the context, just like this does a selecting of the token kind. Creating it automatically selects this as the operator set, and so each of these gets added to that operator set, and then I can use that operator set as an atom to do operations on, to build expressions as I want, to make easier ways to write out portions of the state machine later. Uh-oh. I thought I had this on silent. Luckily I don't need to answer. Okay. Sorry. Continuing. Similarly, keyword sets. So keyword is different from a token kind because these token kinds here aren't keywords, right? These are just token kinds. This is a list of keywords. This works a lot like the operator system. I'm still binding what kind of token I want this to be, and I'm saying all of these keywords map to the keyword base kind. It's not assumed that keywords will always map to that. For instance, true and false are keywords that I'm mapping to literal integers, not to keyword. So when you're defining a keyword set, you give them each a name. Like this one up here, there's an implicitly described, like, this is the name of the token. This is sort of up here shows this is the lexeme and it determines the name of the token. Here I give it the name of the token and it determines the name, like the lexeme from it, unless I specify the lexeme. So the reason this is inverted from this is just because I didn't want to, like, because I wanted to use camel case for the names of tokens, so I could have things like align as and thread well, that's not sign of, size of, align of, decal type, right type. I want these to be like capitalized in a way that is sensible, and trying to write the code that takes lowercase words that are like align as all lowercase, right, and figures out where to insert a capital is like a much harder problem than just saying to lowercase the whole thing. So the default rule is you put in a name here, and the lexeme that is associated to that is just whatever you get when you take the string and send all of its characters to like lowercase, right? If that doesn't work for you, you can just assign a separate lexeme field to the key, and then that becomes the lexeme for it instead. So in this way, I define all the names for all the token kinds that will represent my C++ specific keywords, and I defined the set of lexemes that we're going to turn into a table, like I was saying earlier, of true and false, and I gave it this concept of a fallback. So a fallback in a keyword set is basically says, if you don't match anything, I still want you to match, and I want this to be your token kind. So this one does not have an associated lexeme, because this is the catch-all. If the lexeme we are trying to match against doesn't match any of these, then we see if there's a fallback, and if there is, we use it. So it turns out that this is the opposite of something that needs a lexeme. This wouldn't make any sense to have a lexeme. This is the thing that matches all lexemes that didn't match anything else, right? It's a wild card kind of thing. I use this again to do my preprocessors in a separate set. So you can see, like I was saying with operators, I can create separate sets. Here are my main keys, and here are my preprocessor directives. And these, I don't use the automatic naming scheme at all because I want the PP here to be the name of the token, and I want that obviously to be the lexeme for all of those. This also has a fallback that just says, look, I started parsing something that looked like a preprocessor directive, but it turned in, like, the word you gave me didn't match anything I know of as a preprocessor, so that's a problem. You can see that 4coder already does this kind of thing. If I type that, it's like, hey, there's something weird going on here. This is like an error. So this is just pp unknown. It's not necessary. I could have said that that's just lex error, for instance, but I wanted to mark that it was supposed to, it looked like it was going to be a preprocessor, but it's unknown. You can still highlight this like an error. Or you can highlight, okay. So I didn't do this the way I would have liked. This should be default, like base kind lexer error. Okay. That raises a question in my head, because I'm realizing I don't think I ever did key fallback. Just let me look at the constructor real quick to make sure the base kind actually goes somewhere. Okay, yeah, when I add that token, I do actually store the base kind. Okay, okay. See, I didn't remember explicitly doing it, and it's because it just turned out that it was a part of this generic triad token thing that I copied, pasted from up there. So yeah, I did do this. I just forgot to set this guy's base kind to be error, which is, I think, the way 4coder kind of needs it to work. Okay, this, you know, is a sort of a stylistic choice option here. I could call this preprocessor, but then, you know, if I put in a real preprocessor, it automatically goes to 0. I don't necessarily want bad preprocessors to do that. I want bad preprocessors to look like this, and that's a lex error behavior, not a preprocessor behavior. So for the purpose of 4coder usage, that is the way to mark the base kind of pp unknown, I think. Anyway, moving on. This is a special set. This is obviously a little, might seem like overkill. This is a table, this is a table. Why am I doing it this way? Well, I'm doing this way because, again, I don't want to define like a state machine specifically for recognizing define. I still want to have the same basic structure. And so now we have this thing where it's like, okay, the modeling tool was really good. Like, it was, we were able to do like this code. This is what I want modeling code to look like. It's like I have some construct like sm key that I can reuse a bunch of times to get all the features I need. And then this time I'm using it to do something a little bit dilapidated. This is a little bit of a degenerate case, but this is correct for the thing I want. It's just, it looks degenerate, and maybe there was a simpler way to model this, but now I have a choice when I came to add this to the model. Do I want to extend my modeling constructs, or do I want to just make a modeling construct that I already have that's a little bit wrong work anyway? And you always are kind of like, that's why you, like, all of this is constantly like, you're always kind of trying to make your model be close to the correct thing, but being perfect is impossible because it's essentially a compression problem, right? To add a whole new feature to the modeling structure that lets me represent this would be to start doing special casing stuff, which expands the complexity of the modeling or model like generator and the model structure code in exchange for like making a more direct fit between this and what I like to make a more direct fit between what this code looks like and what it is trying to communicate, which is just not worth it in this case. There's one dilapidated degenerate case of this particular modeling construct that does the right thing, and so it feels to me like the right thing to do is to use it in this way. Okay, so that's all of the like stuff that wasn't really part of the slides that I needed to update you on. The rest of this is stuff I already told you about. We have my flags here. Here's my root state that I get by calling begin state machine. The rest of these are all just add states, and they're each a separate state. The reason they're all added at once is because a lot of the times states need to refer to other states. So like a root, for instance, needs to refer to a lot of these. So a lot of them have to be defined before we can actually define the transition cases for root. And then a lot of these need to use a lot of these, and a lot of these need to use a lot of, you know what I mean? Like, there's just like, it starts spreading out into like all, it turns out that you basically, I just want all my states declared right here, so that I can say like, they're all declared and we can refer to them in later code. Now ideally a modeling structure would be better if I could just do out of order stuff. If I could just say root, here are the cases for root, and the cases, some of them will be transitions into states that don't occur yet, but they'll occur later, and I want you to do a type check that's out of order. Unfortunately, I have to define my modeling code in C if I want to avoid parsing, so I have to play by some of C's rules, and this is a case where I just have to deal with this. And so it just means if you need a state that you don't have, you just pop up here and declare it like this. If you have a state you don't need, you pop up here and delete it. There's a little bit of extra work involved in that, but It's as clean as and as like well formed as I can figure out how to get it. With one exception, the other way I could do this is instead of declaring states as like things that I get back from calls like this, I could actually just use states as like strings. Like I could be going like skip all this code, and down here when I say sm select state, I could be saying select root, and when I say transition to like the identifier state, I would say that, and then the constructor code would have the job of like taking each state name and like doing the out of order work itself to connect these things together. I could go that far, but again, that's adding a feature for the sake of compressing out all of this, and it just wasn't necessary. Writing this out by hand wasn't that time consuming, and so I would have been adding an implementation difficulty to get rid of a declaration difficulty when the declaration difficulty was just not as high as the implementation difficulty that would correspond to getting rid of it. Ideally, we would have a modeling system that was generic enough, or like a language, an underlying modeling system that would just have solved this for all possible modeling situations, but we don't. So this is what we're dealing with. In addition to setting up states, I'm doing some of the things I was talking about before. I'm taking the operator sets that I made from earlier, main ops, and I'm doing some operations on them to like get get operator sets that are not about defining sets of tokens, but about defining sets of lexemes that I want to be able to parse together. So you can see I'm taking all of the operators that have the dot prefix and the slash prefix out and storing them into this set. Why am I doing that? Well, these two need separate lexing rules in some cases. These don't always mean that it's the beginning of an operator. This can be the beginning of a float, and this can be the beginning of a comment. So in both of those cases, I need to look at that character and not immediately decide to go into main ops. But if I see an operator character that isn't one of these two, this is the actual operator set that I can potentially parse, right? Similarly, I need one that's just the strings that start with dot. So this removes everything that doesn't start with dot, and this is because, unlike slash, which is a little bit different, when I do find a dot, there are things I want to be able to, like, I still want to be able to use the operator set system. Like, I want to have an operator set that is basically the set of lexemes that I need to be able to parse if I found a dot that isn't followed by something that indicates it's a float. Okay. And there might be a little bit of complexity in there that I haven't gotten correct, because it is like, again, this is a thing that I'm using less often, and so it's a modeling tool that I decided to add, but it's a modeling tool that is, because it's underused, more likely to be like a special casey, like filled with special case situations that I need to think through. And I'm just now talking about it, wondering if there's a particular case that I don't know if I'm handling that we'll need to look at. Okay, to finish this up, you can see that what my state transition rules look like. So I select a state, and that tells the system I'm modifying this particular state. And then once you're modifying a state, basically all you can do is add cases. So a case is just a combination of two things. One, it's the something that defines the condition under which this case happens. So it can be a string of characters, such that if any of those characters is the input, this case occurs. So all of these letters, underscore and dollar, are the beginning of identifiers. Capital L, U, U, and R all go into what's called these pre-states, because they could be identifiers, but they can also be string prefixes, so we need to figure out if they are one of those things. You can see, like, if I see any of these whitespace characters, I go to whitespace, but if I see a new line character, I go to a special state called whitespace end PP. And the reason I go to that state is because that's well, we'll get to it, but whenever we're in a preprocessor body, a new line ends that, so I need a slightly different behavior for new line. I have a backslash case, I have period and slash. You can see here I'm going to, it's either operator or it's an F number, a float number, and the reason for that is because of the dot. Operator or comment slash, right? And then the rest of the operators here, you can see that the left arrow bracket actually gets removed too. So when I'm using the operator set here, I'm using the operator set to get a list of characters that begin the valid operator. So I want basically, I want something like this or like this. That's the string that begins all operators, and I'm deriving that from the operator set rather than writing it down manually, because earlier I already defined the operator set, so I can algorithmically find the character array from that, and by doing so, I've prevented myself from having to type out all of the characters which can start an operator, which then means if I change my operator set later, I have to remember to go and make sure this is still valid. Now I don't have to do that. This will always be valid because I'm doing it algorithmically. And you can see I'm removing dot, slash, and the arrow sign. So dot and slash are removed for obvious reasons because they are being handled separately, so I don't want two different case handlers that tries to handle them. This is being removed because this has a special meaning if we see it in a situation where we're inside an include body, right? If we're trying to do an include, then all of a sudden the less than, or yeah, the less than sign should be interpreted as the beginning of an include parameter, basically, right? So this, we can see we're doing a case that has a flag check on it. Is include body false? Is include body true? Right? So this is a situation where, as I was saying before, if I see the less than sign, I know that's the input. Now what I have to do is generate a set of actions that does different transitions based on a flag check, which is where I was saying there's a little bit of a glitch in the way I'm trying to mathematize it on that slide earlier, but not necessarily either, because we could, the way I defined it mathematically is actually possible. I can say that we have one single function that says take a character and the state of the flags and the current state. So I know if I'm in root and I see this character and I see this flag, I do know that that's the next operator, next thing I need to transition to. But I don't necessarily want to output the code to reflect it that is the way I'm doing it. I might actually want code that has one code path that does an if on this flag to determine where to transition to, not some more complicated situation you could get into where you use the, I don't know. I think I've described myself as clearly as I can on that. Explaining it more is not going to help. So, the root is fairly complicated, and there's a special rule. I didn't have to do it this way, but I decided that whenever an emit happens, so if we can pop over here, I didn't say this, but whenever an emit happens as a part of the actions, it's required in this model that the next state be root. Now, that's just basically by construction, because whenever you want to do an emit, the way you write that down in the modeling code is you say, hey, I want to do an emit rule here, and the emit rule can say, here's the type I want you to emit. So if I see anything that doesn't fit any of the things that I'm expecting, I emit a lex error token. If I see the end of file token, or the end of file input, I emit the end of file token. If I see, let's see, there's no more emits here. If I get to the point where I'm trying to match an identifier, I can continuously match all of these things here, right? Letters, numbers, underscore, $, and any Unicode character. I treat those as valid continuations of an identifier. But if I see anything else, a number, a punctuation like a parenthesis, I then emit my token, and as I emit it, I check to see if it's any of these tokens. So first I do a handler here that says if this flag, so if is pp body is true, if this flag is set, we're inside a preprocessor body, check to see if the pp keys, which remember the pp keys is that this guy here, the defined, the only keyword that is contextually locked to preprocessor bodies. So now I'm implementing that here in the model as, okay, use this table when this flag is set, and if you match it, emit. If not, then it'll jump down to use this key here, use this key, the table here, and if you match something, emit it. Now this happens to have a fallback handler, so I know that this is always going to either find a match or use the fallback, and the fallback is identifier type, right? And then finally there's here the case I'm using. So an important thing to note here is I'm using a peak instead of a normal fallback. And the difference is because I'm peaking, whatever character triggered this won't get consumed. So when I'm generating the list of actions, it's not actually assumed that I'm consuming it. I have to explicitly state in the list of actions that I want to do a consume. So for anything that is not consumed, or anytime I try to do a peak, that is converted into a list of actions without a consume in it anywhere. And so it'll emit a token but leave that last character for the root to handle again, figure out what it is. So that's basically everything you need to see about the model. Okay? I'll just scroll through some of this. You can see like what other things look like. Preprocessor directives parse a lot like identifiers do. There's this set of states here for finding integer suffixes. There's a set of states. Let me show you some of the flags. We can remember if an integer we're parsing is a hex or an octal representation with these flags. When we're doing strings, we can remember if we're looking at a wide string, a UTF-8 string, a UTF-16 string, a UTF-32 string, or if what we're seeing is actually a character, because it turns out you can parse everything you can parse with a string, or everything that parses a string also works to parse a character, as long as you know that your final delimiter for the character is different. And so by turning that into a flag, I prevented a whole bunch of states, all of these states, from having to be duplicated for a character version, right? Instead, what happens is when you want to make a character, let me go to where I select a state for character. It sets that flag, and then it always transitions to doing a string parsing. So this is kind of where I want to wrap up. I've happened to have stumbled upon a really great example. Raw string is another great example. Whoops, I didn't mean to do that. These are examples of situations where there's I'm actually not sure that this is a good example. Raw string looks like it's trying to consume a quote there. Anyway, well, I mean, fallback peak is still a good example. So whenever we do one of these peaks, we're kind of wasting time, because it means we are not consuming our input, and we're transitioning to a different state that will do the consuming of that input. So as we are building this system out, what we're actually going to do is we're going to run an optimization phase that looks at the list of actions and converts it into a list of actions that always has a consume in it. If you're not doing a consume, then what you need to do is look at what wherever you would transition and see what it would do, and pull that up into your action list, and then keep on doing that until you've either hit a loop, in which case there's an error in the definition of the model. We have a loop where a certain character transitions between a cycle of states that continuously cycles through the same set of states, or the same cycle of states, never consuming the character and therefore looping forever, right? That would be like a bug in the model. As long as we don't find a cycle, we will eventually find a terminator that and by terminator I mean someone who does consume the character. Once you've consumed the character that you read to do your transition function, you can't just keep looking ahead, because you don't know what the next character in the input's going to be. As long as but when you've done a read and you know the character you've consumed, or you know the character that needs to be consumed next, you can keep on appending actions to your action list until you find the action that's actually going to consume that thing. And then you can like shortcut all these peaks into a tighter state machine, and then we can eliminate states that are no longer referred to, or that are now equivalent because of the fact that we did those pushing out the peak things. And then there will be things like this here, where so this does a fallback peak, and that means it always transitions to string. Right? It doesn't have any other cases. It always transitions to string. So really what this is this is just a different way to go to the string state by first doing this action. So what we want to kind of think about when we're doing this is sometimes actions are associated to the transition themselves, like emits here. And that's because when I was sitting down to actually model it, it made sense to say, like, okay, a lot of times there are 3 different ways. Here's an example. There are 3 different things that I can emit from this state depending on what I see. I can emit this, I could emit this, and I could emit this. And which one I do has to do with, flags, the input character, and what state I'm in, right? So it's like there's a lot of value to not having to make a new state for every possible emit action. On the other hand, there are little one-off cases where I need to set a flag, or I think there are a couple other weirder ones that I haven't even told you that we're doing, but there are cases where okay, I want to set this flag and then do some work. And so I put that on the state because it's easier than saying, okay, there's an emit rule that doesn't do an emit, it does a set flag, or there's something other than an emit rule, and so now these cases need to be overloaded on the ability to take an emit rule or a state pointer. They also need to be able to take this other type of action, like a set flag action or something, right? So instead of that, what happens is if you want to set a flag or do a lot of other actions, they get associated to on the entry of a state. And then a lot of times what happens is someone who wants to transition to string but set this flag first does it by entering this state, which sets the flag and then immediately jumps to this state. And what we want to do is write an optimizer that says anytime we have actions that happen on the entry of a state, those should actually get removed from that state's entry list and moved into the transitions into that state from all over the state machine. And that will let us. That's the thing I've referred to a long time ago. So states have this idea of a action or set of actions they perform on entry, and that wasn't included here because one of the very first things I want to do is do the sort of calculus on the or the number crunching, what do I want to call it? The reorganizing of the structure to turn all of these state entry actions into actions that live on the transitions themselves. Okay? So that's what's going on today. That's what the series of videos is going to be about, is turning this model, the one that I somewhat roughly described here with some glitches, and somewhat displayed here to you, but not in its entirety. I want to implement the code generators on this modeling system. Alright, so I'll see you in the next video.